Hello and namaskar. Welcome back to my channel, guys. And in this video, I will be solving a MLT paper. This is December 2023 end term paper. Okay. And after this, I want to be solving any other paper. This paper I am solving just because there are a lot of demand, lots of comment in, basically lots of comments in the last video which I did. Okay. So this is my last and final paper. And let's start the discussion. So the question is, consider a data set, and the data set is this. Okay, given the data set is this, and the question is, what is the first principal component? Okay, so for this question, basically I would like to basically firstly plot the data set. Okay, so let me plot the data set. So I have plotted this here. Okay, so our data points is basically this point, this point, and this point. Okay, there are 3 points. uh yes, so there are 3 points: this point, this point, and this point. Okay, now what PC does, so principal component basically captures the linearity of the data set. Okay, also captures the maximum variance. Okay, so if I want to make a line, or basically it rotates the plane, PC1 is the rotated plane which captures the linearity. So if I want to rotate the plane, okay, the my best plane which will capture the linearity is basically this line, correct? And the points on this line are 1 0 and -1 0, which is the options in our data basically question. So these will be our options. Okay, sometimes you will just capture basically questions like this, you just plot the data set and you will get the answer. Okay, but I also like to basically show you that if you want to calculate, let's say the question came in exam ki calculate the principal component. Okay, then how you will be calculating the principal components. Okay, so given the data set, first you have to centralize the data set, and that is check the mean of the data set. If it is not 0, then you have to basically centralize it. Okay, so what I did, basically I found the mean of these data points. So for first data points, let's say -1 0 and 1. Okay, so -1 0 1 plus upon 3 comma 1 plus 0 plus 1, correct? So it will be again by 3, so it will be this. Now after finding the mean, just subtract it from the data set. Okay, so when I subtracted it from the data set like this, so I get a centralized data set, this, which is this. Okay, now my data is in 2D, so I have to find the covariance matrix, and this is the covariance matrix for 2 by 2, right? If we have 2-dimensional, then 2 by 2, then 3-dimensional, then 3 by 3, right? Now we have to find the covariance of each of these. So how to find the covariance? The covariance formula is this. Put it here like xx. If I have to find, then I have x minus x bar, x2 minus x bar, or x3 minus x bar into my by 1 minus by 1. So basically we are taking xx, so we have to do it 2 times, which is basically square. Okay, so doing this we will get covariance as this. Similarly, we will find for this, this, this. Okay, after finding this, you will get a covariance matrix like this. Okay, you will get this. Now what you have to do, you have to basically find the determinant of c minus lambda I. Okay, basically you have to subtract lambda I from c and then find the determinant. So when you do it, so your covariance matrix will look like this. Okay, so it will basically subtracted diagonally because it is lambda times I. So basically it is nothing but here it will be minus lambda times 1 0 0 1, correct? Something like this. So that's why it will be subtracting like this. Now after that, when you find the determinant, so basically you will multiply this minus this, right? Okay, and after this you have to find the lambda. Okay, so when you calculate the lambda, you will get something like this. Okay, you will get something like this. So our lambda 1, basically the PC1 is the eigenvector. These are basically what? These are basically eigenvalues. Okay, so PC1 are the eigenvectors corresponding to the largest eigenvalue. Okay, so our largest eigenvalue is this, so we will take the lambda 1 as this, and after this we have to find this equation, that is c minus lambda I, basically lambda 1 times I into v equals to 0, and from here we have to find the v's. So basically we have c as this, lambda 1 as this, and I is this, and into my v is basically v1 minus v2. Okay, from here you will calculate the v, basically it is not v1, it's v. Okay, so it's basically v, okay, not v1. So v will come as this. So this now you will say like it should come as 1 and minus 1. So there can be like it will be nothing but approximately it is nothing but 1 and 0. Okay, so it will go to 1 and this will go to 0. So that's why when we see the options and when we plotted, we see that the 1 and 0 and minus 1 0 will be capturing the linearity as you see here, right? So that is why our option matches with that also. But originally when you find, it will come as this. Okay, now I hope you know how to find the PC1. Similarly, if you want to find the PC2, then it will be the second highest lambda. Okay, now next let's move to next question, that is a team was given a data set X from R d cross n, where d are the data, d denotes the number of features and n denotes the number of sample. Okay, they found that there are 20 samples. How many samples? There are 20 samples in the data set. Okay, 20 sample in the data set, and each sample contain 100 features. Okay, each sample contain 100 of features, right? 100 of feature. Assume that the data point x5 to x20 all are in linear combination of x1, x2, x3, x4. Okay, so we are given the data set, okay, with 20 samples. Each sample contain 100 feature, and all these are basically among 20 samples, from 5 to 20 is basically the linear combination of 1 to 4. Okay, so the question is that suppose the team applies a linear PCA, okay, on the data set and reconstruct the data point with zero error using the cake principal component. Okay, zero, it basically what it does, it reconstructs with zero error. Okay, the main thing is it reconstructs with zero error. Okay, then for what value of k the reconstruction error will be 0. Okay, so here we are given with n equals to 20 and d equals to 100. x5 to x20 are linear combination of this. So in PCA, the number of principal component needed to reconstruct the data with zero error is basically equal to the number of linearly independent vectors, okay, that spans the data set. And in this case, we are given that there are 4 vectors which are linearly independent. Okay, it is given in the question. So here, how many vectors we needed? Basically 4. Okay, so the 4 will be the answer. Now, the next question is, suppose the team applies kernel PCA on that particular thing. Okay, using the kernel matrix this on the dataset, choose all the correct options. So first option is the principal direction given by the kernel PCA is same as on the linear PCA. Okay, so basically yes, kernel PCA with linear PCA will give the same principal direction as linear PCA. Okay, it will give the same direction. Next, it says kernel PCA take lesser number of computation than the PCA to find the principal component. So yes, why we use kernel PCA? To basically reduce the computation, right? It is computationally efficient. Okay, so that's why this statement is basically true. Third statement is the eigenvector of kernel matrix K are pointing in the same direction as the eigenvectors of covariance matrix C. So basically, no, covariance matrix and eigenvectors of covariance matrix and eigenvectors of kernel PCA both exist in different spaces. Okay, that's why this option is not correct. And this I already discussed that it will be computationally efficient, not taking more. Now, next question is, consider the layered algorithm used for k-means clustering and choose the correct statement. And the first statement is basically k-mean algorithm may stuck at local minima. So yes, it basically depends on the initialization, how we initialize our centroid. Okay, initially, however we initialize our centroid, it will decide whether it will go to global minima or local minima. Okay, so it may stuck at local minima, so that is true. It guarantees finding optimal clustering global minima in every run. So no, it don't. If we initialize it incorrectly, then it is stuck at local minima, not go to global minima in every run. Okay, if the resources are limited and data set is huge, it will be a good to prefer k means over k plus plus mean. So k plus plus mean is basically solves our initialization problem. It provides a better initialization, and for that it need more resource. Basically, it is computationally it takes more resource than k means algorithm. That's why this correct statement is correct. Okay. Now, in practice, k should be as large as possible. So, no, if k is as large as possible, then there will be a overfitting. Let's say k is basically what? There are neighbors. If I go to each and every neighbor, okay, and ask that whether I am a plus one or minus one. So, whatever the majority of the data set, okay, if majority is plus one, then they say that plus one, okay, but it can be minus one, but as the majority is plus one, like in a whole data set, so it will always give plus one. Okay, so that's why we can't take as much k as possible. Okay, so this option is not true. Next question is, we wish to fit a Gaussian mixture model with k equals to 2 for having a data set having 4 points. Okay, at beginning the tth time step of EM algorithm, we have theta t as follows, where pi given, pi2 given, mu1, mu2 and all this stuff are given. The density of the points given a particular mixture is given to you for all the 4 points. Okay, so density is given. Okay, that probability of x where z equals to 1 or z equals to 2 is given. Okay, what is the value of lambda ik for I equals to 1 and 2 k equals to 2 for eth step? Okay, after eth step. So the formula of lambda ik is basically p, it is nothing but probability of z to be k given xi equals to given xi. Okay, and that is also equals to lambda k, basically pi k into f of xi given z equals to k upon summation of all these pi j into my fxi upon fxi given zi equals to z. Okay, so summation of all j, like z is from 1 or 2, as in this case there are 2, right? So we have to find lambda 1 2, that is basically probability of z1 as z of 1 as 2 given x1. Okay, that is nothing but this formula. Okay, and as I said, below is the j summation of all those. Okay, so basically it's kind of normalization so that our probability will be at 1. Okay, so lambda 1 plus this, lambda 2 plus this, all these values are given here, lambda 1 and lambda 2 and all the values are here. So when you put this, okay, and then solve this, you will get this. Okay, that is our answer. Now, next question. Consider a linearly independent set of data points. This is given and the corresponding labels are given. Suppose we find the data points using a simple linear regression model with the square loss given as this. So this is our loss component, and compute the value of loss. So basically we have to find the value of LW where our weight vectors are given as this. Okay, so let's first find the weight vector. So we have to find the W star, which is equals to x transpose inverse xy. Okay, so first we will find the x transpose, that is this x into x transpose, basically transpose is equals to x, so we will calculate it and it will come as this. After this, we have to find the inverse. When we find the inverse, it will come as this. Don't say that why you are not showing the calculation of inverse, because I suppose you know these things. Okay, these are the basic things you have learned in maths too. After, also we have to find the xy because it gets multiplied in this, you can see here. right? So I found the xy and xy this. Now I will be basically multiplying all this. So this will I will multiply this and I got this, right? 1 by 4 0 1 by 4. You can pause it and basically see the calculation, or otherwise I will provide the PDF on the Telegram channel. So do join my Telegram channel, or also go and follow me on Instagram. Okay, I take questions there, and all I also guide people there. Okay, so just go there and just check it. So now loss is this. Okay, loss is this. So we have to find each this part for each data point. Okay, so for data point 1, that is for x1, we have w transpose x1 minus y1. So w transpose we get like this, which was the above in above calculation, and minus bias by one, which is basically the label. Okay, so when we do the calculation of this, we will get 1 by 2. Okay, for this we will get 1 by 2 minus 0.5, that is 1 by 2 is 0.5, and minus 0.5, so it will turn as 0. Similarly, for W2 you will find, and it will also come as 0, and W3 will also come as 0. So summation, any loss is basically what? Summation of all this. Okay, so when you sum all these losses, that is 0 plus 0 plus 0, you will get as 0, and 0 is our answer. Now next question is, consider a dataset with 3 features and 5 points. Okay, 3 features are there and 5 points are there, given like this. You decided to train a linear regression model on this dataset. After training, you obtain the following weight vectors. You will get this weight vector. Okay, no, now you decided to introduce a L2 regularization to your model. You train the model again with regularization parameter, that is 0.5 for lambda equals to 0.5, and you will get the new vectors, weight vectors, that is this. After regularization application, you will get weight vectors like this. Okay, based on this data set, we have to answer the following question, like based on the given data set using the regularizer parameter. Okay, regularized weight. Okay, we have to predict the y for the following data set. This is the data set. So prediction is basically nothing but y cap equals to w transpose x. Okay, here w transpose will be the regularized parameter, and x is basically given here. So this is our regularized parameter, this is our data set. So this is basically nothing but a dot product. So we will do this and we will get 7.9 as the answer. Now it's saying that further we reduce the regularization parameter to 0. Okay, if we reduce the regularization parameter to 0, then it is nothing but the original parameter which we already had, right? So when we do a prediction with that particular parameter which we already had, that is this. So this transpose into this is basically come as 9.7. So here the answer is 11.9, which is not correct. The answer will be none of these. Okay, so this is the answer. Now next is, consider the following dataset for a binary class classification, and this is the dataset we given. The following tree separates the two classes. Okay, this tree separate these two classes. Okay, so 1 and 0 is the basically two classes. Now question 1 is basically in the form of x less than p. P is basically some integer. So according to that question, basically it separates into two classes. So it is asking how many possible parameters for P. So what I did first, I just sorted it in ascending order. Okay, so I can check that minus 4 it is 1, for 0 it is 0, for 6 it is 1, and greater than 6 it is basically 0. Okay, so I know one thing, that it will be basically x greater than 6, it will be no, correct? So, and for 1 it is basically 4 to 7. So I can take p from 4 to 7, any value from 4 to 7, it will give me 1. Okay, except that 0, basically 0 is a outlier, you can say. So okay, so we have how many values? -3 we can take, -2 we can take, 1 0, all these points we can take, and we will get the decision separated. Okay, so how many points total points are 10. Okay, including 0 as well. So it like not every time it will be perfect. So yes, suppose you have a 4 class classification problem where labels are y from 0 1 to 4. Okay, and the training example xi has binary feature, 3 features are there and 2 points are there, basically 0 and 1, all considered 0 and 1. How many parameters do we need for to classify an example using naive bias? So again, I am reminding you this formula which I have told you in quiz 2 also, that if you want to find the parameter and conditional class is not given, then you will use this parameter. Okay, and if conditional class is given, you will use this formula, and if not mentioned, we will use this with conditional class independent, where D is the feature, K is the classes, and N is basically the outputs 0 and 1. Okay, here in this case. So from here, D is 3, K equals to 4, and N is basically 2. So we will put it here. Okay, so N minus 2, that is 2 minus 1 into 3 into 4, plus 4 minus 1, that is 12, plus 3, that is 15. Okay, so I hope you got it. Yes, next. The figure below displays the sample from the dataset D, where each sample xi belongs to R square. The green points belongs to class 1 and red points belongs to class 2. Okay, so this is the arrangement. Now the question is, suppose we run the perceptron algorithm by initializing the weight vector to 0. Weight vector is 0. Does this algorithm converges with 0 error in a finite iteration? So no, it will not converge to 0, because perceptron algorithm generates basically guarantees to converge on linearly separable dataset. Okay, if the dataset is linearly separable, then perceptron algorithm guarantees that it will converge. Okay, but here we can see it is not linearly separable, right? You can't draw a decision boundary which can separate it correctly with 0 errors. Okay, so here it don't guarantees. Now, next is, consider a logical regression model that has been trained on binary classification problem on a dataset in R2. The final weight vector labeled by the model is this. Given a data point as input to model, it returns 1 as predicted label if the probability is greater than 0.75. Otherwise, it predicts 0. Okay, if the probability is greater than 0.75, then it predicts 1, otherwise it predicts 0. So asking what is the prediction of 0 to. So for note that the probability by logistic regression is basically P of y equals to 1 given x. So first we have to find the W transpose x here. Okay, so W transpose x is basically, we got at this. Now, as this is a logistic regression, that's why we found, like in our logistic regression case, for prediction we have W minus W transpose x here, so that's why I found the W transpose x first. Now P of y equals to 1 is basically this. Okay, and it is nothing but we put it here, and it will give us approximately 0.6968, which is less than 0.75. That's why our prediction will be 0, because this is the probability. Okay, this is the probability which came, it came less than 0.75, and if the probability is greater than 0.75, then it is predicted as 1. If less, then it is predicted as 0. Now, next question is basically related to SVM. Consider hard margin SVM trained on R2 dataset for binary classification problem. Okay, red and green points are belongs to the training dataset. Okay, red points belongs to -1 class and green points belongs to +1 class. The black point is test point. This black point is basically a test point. The dotted lines are supporting vectors, hyperplanes. We don't have access to the test data point during the training. Okay, so this data point we don't have during the training. Okay, this is in test data set. Okay, now question is, which of these following models are basically so equation is the decision boundary. Okay, so when the only way to check which is decision boundary is basically to plot these data points. Okay, so when you plot these data points, so all the three data points, basically all the three equations will be this. Okay, this line, okay, this line will be, all these three data sets are same line, and this is basically this equation. Okay, we can clearly say that this is not a decision boundary because it does not classify this, but these all three are the decision boundaries which classify properly. So these three are my decision boundaries. Okay, and we can do it like basically with the plotting. Now in the same question we have to find the bit of separation between these two parameters. So I took this value, basically there are three decision boundaries. Just take the one which with which one you can find a maximum width. Okay, so I took this, and from here we have w, basically the coefficients. Okay, now to find the norm, basically what we did, we took the norm of this. The norm of this will be come as this root 64 upon 21. Okay, that is 441. Now width is basically 2 upon norm of w. Basically this is 2 upon this, and when you put it and solve it, you will get 5.37, which is our answer. Now consider a soft margin vector machine SVM for a binary classification, and this is the optimized software SVM equation given with the constant this. Now the options. When C is 0, the optimal value of objective function for soft margin problem is 0. So when C is 0, basically we remove the penalty, okay, because there is no error. So objective function will only minimize the norm W. Okay, so this is the correct option. For dataset n, there are 2n constants. So yes, for one dataset there are 2 constants here. You can see that. So for n dataset there will be n 2n constant. A small value of C allows for a large margin, potentially leading to less misclassification on training data. No, it will uh, lead to more misclassification. If C value is less, it will be basically more classification, misclassification. And this I already talked about. Now, the question is, which of the following statements are correct? Underfitting model have high bias and low variance. Yes, because we have discussed that error is basically nothing but bias plus variance, right? So it is nothing but bias variance trade-off. So underfitting, if the model is underfit, then it will have high bias and low variance. I have discussed in my lecture also, so you can go and refer to that also. And overfit means low bias, high variance. Okay. Generally, weak learner in the random forest are tend to underfit. No, they reduce variance. Okay, and that's why they improve performance. They don't underfit, they improve the performance. If the performance of each estimator in the bagging algorithm is almost identical, the benefit of bagging combines them may be minimal or insignificant. So basically, bagging is beneficial when there is a diversity in the estimator. Okay, so this is basically right to say that it will be minimal or insignificant. Okay, in random forest, multiple decision tree are trained on the simultaneously, allowing for parallel processing and faster model training. Yes, because random forest is based on bagging algorithm, and you know that bagging is can run parallelly, right? It can do parallel processing, but boosting can't do parallel processing. So you have to remember this, and these things I have discussed in my lecture also. Suppose we have trained our 4 models using the same training set from the dataset and recorded the error. Okay, for same training point we have used this. The training error for each model will also recorded using a separate dataset. The record values are summarized in this table. Okay, based on this we have to find basically tell the outcome. Okay, so first, in the first model you just see that training error is this and test error is this. So training error is very less, but testing error is very high. It means that our model must have overfit in our training data. Okay, that's why like in training data it is giving good accuracy, but in test data it is overfitting. Okay, so we know that we can conclude that must be our data is overfitting. Similarly, it is correct. It look good, but in this case you can see that the errors are way high, right? Here you can see the 0.21 and zero point 0.5 errors, but here it is 5.9, 6.3. It means that in training error also the error is high, and test error also the error is high. It means that we have underfitted the data. That's why in both the cases we are getting a error as maximum. So model 4 tends to underfit and model 1 tends to overfit. Consider binary classification problem. Suppose that we have 10 samples. Each sample is being positive or negative. Suppose the squared error is given this. Which of the following loss function can be greater than 10? So which can be? So it is a linear loss function. Okay, that is a regression loss function. You can say linear loss functions, and loss function will output wide errors. That's why the error for 10 data points can go more than 10. Okay, because we are 10 samples, right? Now, second is basically logistic regression error function, and it will generate basically 0 or 1, either 0 or 1. So with 10 sample, it can maximum go to 10, but we want greater than 10, so this will not go beyond that. The sign of double transpose xi is also the same thing, logistic regression thing, and again same, it can produce maximum to 10, so it won't get go beyond 10. Okay. Next, choose all the correct statement about the neural networks. It can use both regression. It cannot be used for both regression and classification. No, it can be used for both regression and classification problem. It can have more than 2 layers. Yes, there can be multiple layers. That is known as deep neural networks. Okay. The activation function have to be non-linear to separate non-linear data points. Yes, it is correctly uh, said. Each neuron in the neural network may or may not have bias associated with it. It is not mandatory in the neural network to have bias. We have already said when we are taking example that it is not necessary to have bias in our neural network. Okay, so yes, this is the pretty much it. This is the whole paper, and you will get the paper link in the description as well, and also on the Telegram channel if you have already joined. If not joined, then please join. Also follow me on Instagram. All the social link will be given in the description on that link tree. Okay, so go and follow me, and please subscribe if you haven't subscribed, because we are close to 5,000 subscribers. So that's it from this video, and see you next time.